For this lab, I have 3 goals. First, I want to investigate how U-tapes work. To do this, I will create U-tapes and observe their interactions with my hands and with the neutral book. Secondly, I want to determine the sign of the charge on the U-tapes. By observing the interactions between U-tapes and a negatively charged object, I can determine the sign of the charge on the U-tapes. Finally, I want to use this information and 2 U-tapes together to approximate the charge on 1 U-tape. This experiment will focus on these two physics models. The first is this equation for the electric force, which is equal to the electric field and the charge times the charge at the observation location. The electric field equation is below as well. The second is Newton's second law, which provides that when the change in momentum is 0, the net force must also be 0. Electrical force. For the first aim of the lab, I began by setting up 2 U-tapes next to each other. These tapes repelled each other, as you can see in the picture to the left. Then I moved a book, a neutral object, near the U-tape. In this case, the U-tape was attracted to the book. To determine what charge the U-tape has, I used this pen test. I rubbed a plastic pen against a blanket so it would gain a negative charge. Then I moved the pen close to a U-tape, which was attracted to the negatively charged pen. This means that the U-tape is positively charged. Now that I know the sign of the charge in the U-tapes, I want to determine the magnitude of the charge. To do this, I set up a U-tape on top of these books. Then I moved another U-tape near it and measured the distance between the U-tapes, at which point the U-tape on top of the book started to float. At this point, the electrical force of tape A on the bottom of tape B on top is equal to the gravitational force acting on tape B. This is based on Newton's second law. Since the change in momentum in the y direction is 0 at this point, the net force in the y direction must also be 0. As you can see from my force diagram, this happened when the distance was 0.02 meters. Then I calculated the magnitude of the gravitational force on tape B by converting the length of the tape to its mass using its approximated density. I set this equal to the equation for the electric force and solved for Q would equal. Then calculations, I used the charge of an electron to find how many electrons deficient the U-tape is. Then I found how many atoms this would approximate to. Finally, I calculated the ratio of electrons to atoms. Each of my calculations for each of these steps can be seen in this picture here. Floating and scale factor. I did this code to calculate the charge the U-tape would have based on the same principles that I used to calculate it using experimental data. My calculations assumed that there was no air resistance, the charge distributed across the tape can be taken to be a point charge, and that both U-tapes had the same evenly distributed charge. Here my code shows a similar calculation process as what I did when I calculated them on my own using experimental data. For this point, these are the results of my GlowScript code. That the charge the tapes must have is 2.97284 e to the negative 7 coulombs. This is less than the charge I had calculated, but it is within the same scale factor of 10. This could be due to experimental error from having difficulty in fixing the tapes with as little contact as possible. Another possible source of error could be that there was a slight angle to tape B because the tops of the books did not match exactly, which could have skewed the distance. If the signs of the charges of electrons and protons were switched, the interactions with the U-tapes would remain the same. Like and unlike charges would still attract and repel. And finally, because hands are conductors, they can transfer the charge on the U-tapes, making them unusable for the experiment. So it's best to limit how much the tapes are touched to preserve the charge as much as possible.